Hello everyone, welcome to another tutorial on RA series MCUs. In this episode, we are going to show you how to design a frequency counter using high-speed comparators in RA chips. So, let's say there is a sinusoidal signal with a fixed frequency and we would like to measure it. How do we do that? Well, one method is to make use of a high-speed comparator module to track the zero crossings. What we mean by this is whenever the sinusoidal signal is crossing over from positive to negative or the other way around, we can register that timestamp. The program will basically rely on the callback function that is called when the state of the comparator changes. And these changes are triggered at a level set by the user, which in our case is the baseline level of the signal. Whenever the comparator callback function is called or a zero crossing is made, the time since the last zero crossing is taken and multiplied by 2 to get the time period of the signal, which then gives the frequency of the signal by inversion. Now, you must note that only certain RA MCUs support these high-speed comparators, and for our demo, we are going to use the RA8D1 MCU and this evaluation kit. The connections for this will require one signal input that is connected to the P004, which is an ADC pin. Let's dive into the project then. We shall open the E-Square Studio. We want a project for the RA MCU, so we will find the RA project options. Select RA CC++ project and click Next. We will then give the project a name and then enter the project settings. We shall keep the FSP version to the latest as possible. As the platform, we are going to select the EK-RA8D1, which will also locate the actual MCU part number used on these boards as shown in the device choice. Then we will proceed with the default settings. It's going to be a flat project, executable, and bare metal minimal configuration. Once the project has loaded, we shall open the configuration.xml file, which will then open a graphical interface to modify the project settings. Let's start by adding the stacks. Our first stack is the high-speed comparator stack, which is to be found in analog category. Then we add the ADC stack, which will be used to capture the input from the signal source. And then we will also include a DAC stack, which will be used to produce a reference analog signal for the comparator module. To start with the comparator stack settings, we will first change the name and remove the 0. It's not essential, but we shall just keep it like this. Then we will enable the pin output and name a callback function. We will also set the interrupt priority for this peripheral. After that, we are going to have two important settings. We need to define the pin which is being used as the analog input signal port. In this demo, we are going to use the AN000 of channel 0. For the reference voltage, we shall assign the DA0 pin. That's all about the comparator peripheral setting. We move on to the ADC peripheral next. No changes to be made in the general settings. The first setting to be set is the input channel mask setting, where we need to check the channel scan mask. So we shall check the channel 0 and channel 1 as they are available on this MCU, although we are going to make use of only channel 0. No further changes to this peripheral. We also note that the pin 004 is assigned to AN000. Moving on to the DAC module, we will first need to enable the internal output option. Then we have to make a very important setting. The DA pin is not assigned, so we need to do it from the Pins tab. We click on the small arrow and it will take us to the Pins tab. We can see that the operation mode is disabled. When we enable it, we notice some red cross, which means this pin cannot be assigned to DA0. So we look for the individual pin setting and see what's going on with the P014 pin. Looks like it is assigned to one of the ADC channels. So we click on this arrow and that should take us to the ADC pin settings. From here, we simply unassign pin 014 from AN007. Now going back to the pin 014, we will see that it has been assigned to DA0 channel. Double checking on the stack settings, we will notice that P014 is now assigned to DA0. Now, we are ready to generate the project contents. That is, the project will be configured with the peripherals we have just selected. In the Developer's Assistance menu, we will see that the peripheral APIs have appeared. Now, moving to the HAL entry file for the programming part. We will activate the C++ perspective for a slightly better view. Starting with the code, we will first declare a float variable frequency that will store the value of the calculated frequency. Then we will define a division factor macro. This is basically dividing 1 by the clock speed of the PCLKD component, the clock of the timer module. We can check for the value from the clocks tab. Then we will declare variables I and j and initialize their values to 0. These are to be used as counters. Then we will declare two integer variables. These will store the timer cycle values and another will store the raw ADC measurement values. We need two more macros. The macro defining the DAC values for reference voltage. In this case, it is a 12-bit DAC, so 2045 is somewhat equivalent to 1.65 volt, which is half of the maximum 3.3 volt. Then we will simply use the macro channel 0 to refer to the channel number for the ADC, which in this case is the value 0. Okay, we are done. We can now proceed to the HAL entry function. As usual with these projects, we will declare the FSP status variable and then we will declare a comparator specific variable, stabilize time, and set the value to 0. This is required for one of the comparator APIs we are going to use later. In the next few steps, we will implement a number of APIs from the peripheral modules. First, we want to open the DAC module, so we simply call the relevant API from the developer's assistance and follow it with an assert macro. In a similar manner, we will bring in the API for ADC and comparator modules. Once the modules are initialized, we will then implement an API to set the DAC value, the DAC_write. Once we insert this API call, we can use the DAC value macro here. Next, the ADC scan configuration is implemented, followed by the DAC start. Then we will call the getComparatorInformation API and pass in the pointer to the stabilization time variable as argument. We will add a little delay here based on the stabilization wait time value for this particular comparator, which would just have been updated during the previous API call. We will then declare an ADC status variable, which is a structure defined in the ADC peripheral header file. The next API call is regarding the comparator output enable. Then we shall write some codes to initialize a timer module. We will use the RBSP module start to initialize the GPT timer and then reset the counter values. We will then make a while loop. The loop starts by initiating an ADC scan using RADC scan start. After starting the scan, it reads the ADC value from channel 0 using ADC read and stores the result in ADC measure. Our Hall entry function is now done. The next step is to define the callback function for the comparator. We can insert the basic structure for the callback function from developer's assistance. We will start with the if statement that checks the value of I and starts the timer. In the next callback, the value of I is not 0, so it will acquire the timer counter as well as reset the timer. The frequency will be also calculated here. Basically, at every transition of the comparator state, which is when this callback is executed, the timer is reset, followed by a reading in the next transition, and the cycle goes on. As we have finished writing the code, let's try to implement the project on an array board. We try to build first. There seems to be an error. Let's see. Looks like there is something wrong with the stabilization time structure. Okay, so this is a structure and the value given is missing the curly brackets. Once we place the value inside the curly brackets, it should be fine. Alright, it has built without errors. Let's try to upload it. We will hook up a signal generator to the board as shown here. Connect the signal pin to P004 and make sure both share the ground. So we upload the program using the debug option, and we shall place the frequency variable into the expressions tab, enable real-time refresh. Our signal generator is set at 100 Hz. We click on the resume button twice to start. And we can see that the value in frequency is around 100 Hz. Let's try changing the frequency to 300 Hz. Okay, now 400 Hz. Let's bring it down to 90. Great! Seems like we are getting some good readings on the frequency of the input signal. So folks, that's all we have today. You can build your own frequency counter using this comparator technique. See you in the next video.